In this video, I'm going to be telling you about Riemann sums, which is going to be our kind of first steps down the road of finding the area underneath a curve. And so to start, I would point out that, looking at the graph on the left here, if the graph of G consists of a quarter circle and 3 lines, we can compute that area using geometry. Okay? We could compute that using probably the area of a triangle plus the area of a quarter circle plus the area of another triangle plus the area of a rectangle. We could figure it out if we had to, right? But we wouldn't have any way to deal with the area between this curve and the x-axis between just two x values. Okay. So before I start, though, I am going to talk a little bit about notation. Okay. So for both of these, suppose that this was 2 and that's 5. This area right here that we don't know how to compute yet, we're going to denote that area with the integral from 2 to 5 of, if this is a curve f of x, maybe I'll write that in there. If that's a curve f, then this is going to be the integral from 2 to 5 of f of x dx. Not really sure what we mean by all this quite yet, but that's what we're going to call that area, and we'll be learning this unit how to compute that. Okay. Today, we're going to not actually find the exact value of this area, but we're going to approximate this area using Riemann sums. All right, so what you need to know is that a Riemann sum for the area under the graph of f and above the x-axis is given by a sum of rectangles, right? Sum of heights multiplied by width. And the heights of the rectangle are given by, the function, the height of the graph. And the width is going to be, well, we're going to have to divide that interval into little sub-intervals, and they'll each have their own respective widths. So let's just actually get in towards doing that a little bit. Let's approximate the amount of area under the graph of f of x between 0 and 2 using a left Riemann sum and a right Riemann sum. Okay. Now, I'm going to suggest that we use 4 subintervals of equal width for this, because first of all, because we're just starting, and also because, it'll make the numbers work out nice. So what I'm going to do is I'm going to approximate by taking 4 rectangles that are, I'm going to get the height of the rectangles from the height of the graph of f, and I'm going to find the areas of those and use that to approximate the area in general. Okay, so what I'm going to do is I'm going to divide this in half first. That would be 1. Then I will subdivide those in half, and that will be 0.5 and 1.5. And when I go to do a left Riemann sum, the value of the function I take is going to come from the left edge of each subinterval. That's one way of saying. So what I'm going to do is I'm going to be considering, maybe I'll do blue, switch up the color. I'll do the left edge of the first subinterval. I'm going to take where the graph is, and I'm going to use that as my height. That's my first rectangle. We see that that's a decent approximator for the amount of area underneath the graph of f between 0 and 0.5, but it's not great because there is this leftover area, but we'll talk more about that later. Then for the second subinterval, I'm going to go with the left endpoint of that subinterval, which will be 0.5, and then I'll have a rectangle there. Okay. And I'll just keep doing that until I've covered the whole thing. Right, and then the fourth one will come out here. All right. And then I can compute those areas by taking height and multiplying it by width. We know how to find the area of a rectangle, and then we're going to add them all together. We can see it's pretty clearly going to be an underestimate. But, okay, let's think about the height of the graph at these various points. This height here is going to be 4 to the 0 power, because it's the height of the graph of y equals 4 to the x, where x is equal to 0. This right here will be 4 to the 0.5. That will be 4, and this will be 4 to the 1.5. Okay. So we're going to need to be able to compute 4 to the half and 4 to the 1.5. I'm pretty sure you know what 4 to the 0 and 4 to the 1 are. Okay, but we need to be able to do those too. Okay, so the amount of area under the graph of 4 to the x as x runs from 0 to 2 is going to be approximately what I get when I add these rectangles' areas together. Okay? So it's height times width. So height was 4 to the 0, which is 1. Width is 0.5. Hey, I'm pretty sure I have not yet mentioned that this figure is definitely not drawn to scale. If I had actually drawn 4 to the x, it would have been so tall and narrow it would have kind of lost its meaning. So it's really not drawn to scale, right? Oh, you can really see this. This is 2 and that's 4. Something's off, but this, yeah, figure not drawn to scale. Plus the second one has height given by 4 to the 0.5. I'm just going to point out that 4 to the 0.5 is 4 to the 1/2 power, which is 2. So this is 2 times 0.5, plus the third one will be 4 to the 1st power, and we know that 4 to the 1st is going to be 4, plus, and then the last one I'll have 4 to the 1.5 is 4 to the 3/2. That's equal to the square root of 4 to the 3rd, and that's 8. So that's going to be 8 times 0.5. Okay. And that's a left Riemann sum. Okay. Notice also that for a left Riemann sum, the left edge of each rectangle is touching the graph of the function that we're trying to approximate its area under, the area underneath. Okay, so I think that's a left Riemann sum, and I would say that if we needed to actually use this later, or if it was multiple choice, we would need to put these all together, and we would get half plus 1 is 1.5, plus 2 is 3.5, plus 4 is 7.5. But in the free response section of the AP exam or on the quiz or something like that, we are free to just leave it as an expression like this that is equivalent to the right answer that's a real number. Okay, for a right Riemann sum, it's going to be very similar, except we're going to use right endpoints. Okay, so I'm going to subdivide my interval. That will be 0.5, 1, 1.5, and 2. Maybe I've subdivided it a little better. I'm going to just make sure that, because I'm over here pretty near the edge, I'm going to just make sure that my lines are straight. All right. So it's right Riemann sum. I kind of like to start from the right. And so we start the right endpoint of the subinterval is the representative we're going to use. So we're going to say that we're going to go, and I'm going to actually use a straight edge because it's a really long line to draw. I don't want it to look bad. All right. All right, that's one of our rectangles. The second one will take its height from the right edge of the subinterval, so from 4 to the 1.5. And I'll go and do this one also. Might as well just use a straight edge for all of them if I'm going to use it for some of them. Okay. And then for 0.5, we'll go up here. Right. And then the last one, pardon me, I got a little crooked. It's right here. I think I trust myself to draw. Oh, I did that and it wasn't very horizontal. Okay, there we go. And that's going to be our right Riemann sum, or an image of our right Riemann sum. So using a right Riemann sum, I'm going to say that the integral from 0 to 2 of 4 to the x dx is approximately equal to, okay, I'm going to use the right endpoint, so 4 to the 0.5 is 2 times 0.5, plus this height is 4 to the 1 power times 0.5, plus here I'm taking 4 to the 1.5 power, which we had previously said was 8. And the last one has height 4 to the 2 power, so that's 16 times 0.5. Okay. If you add these all together, you're going to end up getting 15. And so, you know, between 7.5 and 15 is kind of our range. right? Because we know this is an underestimate and that's an overestimate. Okay, but that's not a very good range. Okay, if we wanted to improve our estimation, what we would want to do is, one thing we could do is just add more rectangles, right? Just subdivide into even smaller intervals so that these gaps here, or these extra bits here, they get smaller. But that's not something we're going to do right now. We're just going to find a Riemann sum for a given curve and a specific number of subintervals that they're probably going to tell you in the statement of the question. All right, so let's do some table examples and bring in the other two types of sums you can be asked to do in AP Calculus. Okay, we're going to approximate the integral from 1 to 1.4 of g of x dx with a midpoint Riemann sum and two subintervals of equal width. Okay, especially for a midpoint Riemann sum, I recommend that you draw the interval 1 to 1.4. Maybe I'll do that right here in a light blue or something. Let's see, I'm going to need some more colors though if I'm working all of this under the dot cam. 1 to 1.4, and it said two subintervals of equal width. So here we go. That's 1.2. If we're going to do a midpoint Riemann sum, the representative that we're going to choose, just like with a left Riemann sum, we chose the left edge of the interval. With a right Riemann sum, we chose the right edge of each subinterval. With a midpoint Riemann sum, we're going to choose the midpoint of each subinterval. And so my representative is going to be 1.1 over here and 1.3 over here. Okay, I'll draw you a picture of what's going on. Let's say here we've got, I actually don't want to do it on this. I'm going to just draw it a little different. Let's say here. There's 1 and there's 1.4. And again, this is not going to be well drawn to scale, but you know, it does most of its increasing early on. I'll say it looks like that. And what's happening here is that we've divided divided the interval into two subintervals, and we're choosing the midpoint, which is happening here and there, and we're using that as the height. So it kind of, that would have maybe was one thing that you were thinking to yourself when I was like, oh, what's one thing that we could do to make this approximation more accurate, is that instead of going on the left edge to the right edge, we could go in the middle so that there was some overestimate and some underestimate. So it's a better approximation than a left Riemann sum or a right Riemann sum. The catch is that it can be hard to compute. So we're going to, what are we going to do here? Okay, we're going to just, we're going to actually do two rectangles. So the integral from 1 to 1.4 of g of x dx is going to be approximately equal to, okay, width of this rectangle is going to be 0.2, and the height is going to be g of 1.1, which is 10. So it'll be 10 times 0.2 plus, okay, the height of this rectangle is going to be g of 1.3 is 13. And then the width of this subinterval is also 0.2 because it said two subintervals of equal width. Okay. And this is the type of thing, if you have a calculator available to you, you can do that. If you don't, just leave it like that, right? Okay, and that's a midpoint Riemann sum. Now a trapezoidal sum. A trapezoidal sum is honestly probably the best for most curves. Okay. It's going to be much more accurate than a left Riemann sum or a right Riemann sum. Maybe I can bring back these two and just give you kind of an idea of what a trapezoidal sum would look like. Maybe on this one I'll do that. That would be where we would just connect these 2 points with a straight line. Right? And then, whoops, that was supposed to be a straight line. And then we go up here. And so you can see that it's a slight overestimate, but it is so much closer than a left Riemann sum or a right Riemann sum. And so a trapezoidal sum, provided your function is not like wildly changing directions in the middle of the interval that you're trying to sum over, it's going to be a really good estimator. And that's what we're going to do here. We're going to use a trapezoidal sum with the 4 subintervals indicated by the data in the table to approximate the value of the integral from 0 to 10 of h of t dt. We can do this. Okay. think what I need to do is maybe I'll just show you one of these trapezoids. Okay, maybe this is 0, 2. Again, this is not going to be drawn to scale, but I think I want that to be 1. I'm going to need more room. That'll be 2. Okay. And then this is going to be 66 and then 60. Yeah. So that means, oh, goodness. No, I did want that to be 2. I was just being foolish. Pardon me. Did just work this example like 15 minutes ago, but whatever. It's not a huge deal. Okay, I'm going to say that's the point at 0, that's the point at 2. So the trapezoid is going to, it's going to look like that. That was a pretty bad drawing, but it's okay. And this has height 66, that has height 60, that has width 2. Okay, I've found in the past that, y'all know how to find the area of a trapezoid. You took geometry class. It's a little easier if you think about it like laying on its side, right? Where we used to average the bases and multiply by the height. Okay, it's still what we're going to do. We're going to average the 66 and the 60 and multiply by the 2. Okay, so I'm going to come in here. 0 to 10 of h of t dt is approximately equal to, okay, this first trapezoid is average the bases multiplied by the height, which is now a width. Plus, okay, and the width was 2 from there. But the next one will have a width of 3, and the 2 bases will be 60 and 52. So 1/2 times 60 plus 52 multiplied by the width, which was 3. I realize I'm probably going to run out of room if I keep going like that, so I'm going to just add in. The third subinterval is 5 to 9, so width of 4, 52 and 44. Yeah, width of 4 plus average 44 and 43. And multiply by the width of that one, which is 1. And that's going to be an expression that's equivalent to a trapezoidal sum for 4 subintervals indicated by the data in the table. Or for the integral from 0 to 10 of h of t dt. Okay, that's great. Okay, now I've got some other examples. And I think what I'm going to do is I'm going to come back on these at the end. I'm going to just do another left Riemann sum and another right Riemann sum. But really want to do is these notes, and these are notes from an old, like 4 or 5 years ago. And so we've already talked about this. The area under the graph of f between x equals a and x equals b is denoted by the integral from a to b of f of x dx. But that's not a bad thing to point out. Okay? Properties of the definite integral. Okay? Definite integral is not a word that I have used up to this point, so I think I need to tell you what do I mean by a definite integral. A definite integral is one that has the bounds of integration on it. It corresponds to an area under a curve. It is equal to a real number. An indefinite integral is what we studied in the last unit where we were just taking antiderivatives. We use that same integral symbol, and that's kind of curious, right? Why are we using the same integral symbol for this area situation as the antiderivative situation from the last unit? And that's what you're going to learn next time. But this is a definite integral. Indefinite integrals don't have the bounds, and indefinite integrals give you a family of functions, as you already know. Okay, so if we take the integral from a to b, and this one you just need to draw a picture, and say we've got a function f. Right? If I have the integral from a to b, which is going to be an area I'll color in red, plus the area under f between b and c, which I'm coloring in blue, if we add them together, this is like the total amount of area under the graph of f between a and c. The integral from b to a of f of x dx is the negative of the integral from a to b. Okay. On one hand, you could look at it as kind of like, oh, the Riemann sums, the rectangles, they had, we all of a sudden went backwards. Maybe we had smaller minus bigger, or we had negative widths of our rectangles. If you don't like that, then just wait till next time. I'll have an even better reason for you to believe me that this is true. Negative of the integral from a to b of f of x dx. Okay. The integral from a to a of f of x dx is just the amount of area like right there on that line. And a line doesn't have any area, so we're going to say that's 0. And then the integral of a number times f of x with respect to x is going to be that number times the integral. You could think about the effect of multiplying f of x by a number. It would scale it up, and so it would scale the area the same way. Okay, I think that's the best way of thinking about it. We'll also see that, well, we already are seeing that an integral is corresponding to a sum, and we can factor a constant out of a sum. That's another reason. Okay, these are use a midpoint Riemann sum in 3 subintervals of equal width to approximate 0 to 3 of 4 to the x. Okay, that's kind of where I got that example from. I think it's a good one, but while we're here, might as well just do all the examples. So, midpoint Riemann sum and 3 subintervals for 0 to 3. Okay, I divided it up into 3 subintervals. Okay, a midpoint sum, I'm going to take the midpoint of each subinterval. And I know I was using that light blue pen for that one, so I might as well just keep going with that. And that happened here and there. Okay, so my height will be 4 to the 0.5 for this rectangle, 4 to the 1.5 for that one, and 4 to the 2.5 for that one. Oh man, 4 to the 2.5, that could be troublesome, right? But I think that'll be 2 to the 5th, which is going to be 32. So we got that. Okay. Yeah, I'm going to say that is approximately equal to height times width. So height is 4 to the 0.5 is 2, times width of that rectangle is going to be 1, plus height is 4 to the 1.5. We've already discussed in this video why that's 8. Width is going to be 1, plus 4 to the 2.5 is going to be 32 width. If you're unsure about that, remember that 4 to the 5 halves equals the square root of 4 to the 5th power, and that's 32. That's why that is 32. And that's going to be a suitable expression for us, right? We could say it's 42, or we could just say it's that. Okay. Will left Riemann sum overestimate or underestimate the value of the area under the graph of square root of x between 0 and 9? Well, that's an interesting question. Hopefully with these next 3 examples, we'll develop rules for when it's going to be an overestimate and when it's going to be an underestimate. Okay, we know what the graph of square root x looks like. It looks like that. And maybe we'll say 9 is here. What I've found is that if you're trying to determine if it's going to be an underestimate or an overestimate, fewer subintervals is the way to go. Like, I go with 2. So a left Riemann sum, I'm going to go left edge, and I'm going to cut it in half. So left edge, that's my rectangle. That's my first rectangle. Has no area. And then my second rectangle, I use the left edge, or the left edge. My rectangle is touching the curve, however you want to think about it. And then I get, okay, pretty clearly an underestimate. And I'm realizing I used the opposite color, but whatever. Okay. And it's specifically an underestimate because of the graph going up, right? It's not the curvature, because if it had been smiling and going up, the left edge would still be, lower than the right edge would be if I'd used right Riemann sum. Okay, so I'm going to say underestimate because square root of x is an increasing function. Meanwhile, will a right Riemann sum be an overestimate or an underestimate for the value of the integral from 0 to 3 of e to the negative x dx? Well, that's another thing that we could just draw a little sketch of. And we know that it's coming from above and exponentially decaying. So maybe that's 3 right there. And if I used a right Riemann sum, 2 subintervals, I think, is what you want to do. It's the way to go. Because it makes it more obvious. There's a larger error. Okay? And this one is also going to be an underestimate. Okay? And this is because e to the negative x is a decreasing function. Or at least it's decreasing for all x, but specifically because it's decreasing between 0 and 3. Okay. What's going to happen to trapezoidal sums on both of those two integrals? Okay, we can draw ourselves a little sketch. Okay, yeah, trapezoid. I just recommend fewer. So I'm just going to do one trapezoid. Right? Take it to the extreme. Just do one. See how that treats you. So one trapezoid here is underestimating. I guess it was really a triangle, and over here the trapezoid is going to overestimate. Because of the curvature, though, right? Because it's curved back this way, because it's concave up, I'm going to say that trapezoidal sums overestimate this one. Because the graph of e to the negative x is concave up. Okay? And this is going to underestimate of x has a graph that's concave down. That is not e to the negative x, that is square root of x. Okay. Now, if f of x is, we're going to separate this over increasing, decreasing, concave up, and concave down. And we're kind of just going to go back to what we found out here. Okay, a left Riemann sum underestimates an increasing function. Okay, so I'm just going to say left Riemann sum underestimates, so I'm just going to put under. And a right Riemann sum is going to overestimate it, right, if we think about what would happen there. And the increasing and decreasing behavior has no impact on the quality of the trapezoidal sum. Okay. So I'm going to just kind of cross these out because they aren't contributing. Hey, later we'll find that that concavity doesn't contribute to left and right Riemann sums. You can kind of see that. If you can't, just draw your own picture. Draw a picture of an increasing concave up function and draw a picture of a increasing and concave down function, and then do left and right Riemann sums. You'll see the same thing happens. Okay, it's going to be the opposite for a decreasing function, right? That's what we saw. So this would be concave up for trapezoidal was an overestimate, and concave down for a trapezoidal was an underestimate. Okay, I think, I'm going to go back and do the 2 more examples. All right, now it's time for you to practice this on your own. So what I'm going to do is I'm going to encourage you to pause the video, work this one yourself, and then check your answer against mine, because it's going to just pop up in like 5-10 seconds. All right, there you go. Okay, so I just used the left edge of each subinterval, so that's why I used 1340, 1190, 950, and 740, and then the width of each subinterval was 1, 2, between 1 and 3, 3 from 3 to 6, and 2 from 6 to 8. Okay. All right, the last example I've got is an airplane burns fuel at a rate of R of t gallons per minute. Approximately how many gallons of fuel are burned in the 90-minute interval? Use a right Riemann sum to approximate it. And just like the other one, you're going to want to pause and work it yourself and check your answer against mine, because it's just going to pop up here in a second. Okay, there you go. So I chose the right edges of each subinterval, which is kind of tough when we list the table vertically, but that made me end up taking these R values, okay, for my heights. And then my width was, the width of each of these subintervals, which went 30, 10, 10, 20, 20. Okay. That's how we do Riemann sums. Okay. I think that's all I got. That's all the examples I got for you. You just need to practice this some, and then this is something that we'll be strong at. But thanks for watching.